Now, many of you may remember a full-time speaker, Bartosz Szurgot. He's been with Code Dive since the beginning, and again, he's back by popular demand. We actually considered talking him out of speaking again, but then we remembered what a fantastic presenter he is, and here we are, Bartosz is with us again. His professional labels are C++, Linux, and DevOps. Also, he's an expert in electronics, 3D printing, cybersecurity, algorithms, computer networks, vision systems, and artificial intelligence. He has been a speaker at many conferences and geek gatherings, including NDC Oslo, EMBO++, Wrocław's first C++ user group, and TEDx. After Hour, Bash contributes to the open source world on a daily basis. He has also co-authored multiple articles in Programista and Software Developer Journal magazines. So, 3D printing programmer's perspective. Bash, go ahead.
Okay. So, hello everyone, and welcome to 3D printing as seen from the programmer's perspective. As said, my name is Bartosz Szurgot, but I'm typically referred to as Bash because this happens to be a concatenation of first letters of my name and surname together, and also for a second reason, because I'm a total nerd who loves Linux, and I'm also a C++ developer. Interested in DevOps movement. So aside from all of the interest that Adam presented, actually there is one more interesting on the list, which is 3D printing, and this will actually be a theme of today's talk. So at office hours, I work at QIAGEN, where I hold the position of a principal software engineer. So I can proudly now say that I work in the highest building in the entire city, even though the office is just on the first floor, but hell, you can't have everything, as they say, right? The name QIAGEN might not really ring a bell, but if you ever gave a blood sample for analysis, there is a really good chance that it has been processed with QIAGEN devices, chemistry, or both. So the name is well recognized in the medical industry. And the medical industry is actually something very interesting because it's probably the only industry in the entire world in which, where you get a positive result, it actually can mean a bad news for you. So working out there, here in Wrocław office, we are mostly working on software for devices for medical purposes and scientific purposes, including but not limited to those who help fight current ongoing COVID-19 pandemic. After hours, well, I'm a parent now, so most of the time I just try to get some sleep, like any sleep whatsoever. But still, I wouldn't be myself if I wouldn't try to nerd out at night anyway. And nowadays, it happens a lot around 3D printing. And this is, and the 3D printing is actually something that I would like to talk to you about today, but not just the 3D printing as seen through the eyes of the software engineer. Now, I promised this will be an introductory talk, so let me start with a little bit of introduction about 3D printing itself. So first, let's start with the high-level overview of the whole process. So first, you design a model on the computer, just like regular 3D mesh. Then you put it onto the printer, which creates it usually out of the plastic, and then you end up with a physical object in your hand. That's like a top-level overview. There are, of course, different ways this creation can actually happen. The common one is fused deposition modeling, or FDM in short, which works by heating up a fiber of plastic and extruding it through the very fine nozzle and putting it layer by layer by layer next to one another in order to create something in 3D. So conceptually, this is very similar to how regular 2D printers work, aside from the fact that we are now adding the third layer, the third dimension. So that's conceptually it, but that's not the only one. You can also have so-called SLS, or selective laser sintering, which works by using high-power lasers concentrated in a small dot to heat up the powder, sometimes metal, and make it a solid in this place. So these are things which usually are found in industry setups because they can actually print in metal. And last but not least, there is an SLA, Stereolithography, which basically prints in resin. There are different technologies available, but the core idea is to have resin, which cures by shining UV light on it. And thanks to this, we can pull out of a bath of resin a 3D printed object. So it's like a third major option that you could use. So let's have a look at comparisons of all these three technologies. So in case of the FDM, the really nice thing is it's cheap and it has great community support with a RepRap project. It's also multi-material, so we can basically select from loads of different plastics to print with add-on of different colors. So there is an enormous amount of material to choose from. The process itself is also very clean. There are almost no leftovers from the print, so no material gets waste. And the devices themselves are really compact. There are, of course, downsides. So first of all, the process is very slow. And the second is very complex. So as long as things go right, it's all cool. But when the problems start to happen, you usually need to have a decent amount of experience and knowledge in order to diagnose any non-trivial issues. The second thing is SLS, so this high-power laser part. So this one is very precise, and the key benefit here is that you can actually print in metal. So this is something that is, for instance, used in the space industry. The resulting parts are really strong compared to plastic ones, for instance, but the devices themselves are really large, are ridiculously expensive. Think of something like a price of a big flat. And the process is also very slow, and most importantly, it's also hazardous. So the powder that is being used to print is actually very, very fine. So if you happen to inhale it by accident, this can be a serious threat for your health. So because of that, you need to have a proper equipment, protective equipment for users of the printer. So this is not something that you will find at homes typically. And the last is the SLA, the resin printer, sometimes called a goo printer. The device is, again, fairly cheap. It's super fast. It's definitely the fastest out of all three. It's like faster by at least a row of magnitude and often even more. It produces very precise parts with a very fine layers. But in reality, in order to print in that, you usually need between 2 and 3 devices, which means additional costs and space. And the chemistry involved is toxic. It's not like deadly toxic, but it's toxic enough that you can get some serious allergies out of it if you are not sitting in a well-ventilated room, if the device is not in a well-ventilated room and you are actually in the different room while the printing happens. So it's not really convenient. It's doable at home, but not convenient. And the process itself is very dirty because the resin usually ends spilling up all over the place, and it's very smelly. So usually you cannot sit within the same room with the printer. So for these reasons, from now on, when we'll be talking about 3D printing, we'll be just focusing on FDM 3D printing. So there are different options, but I think that FDM is most suited for home usage and for beginners. So we'll solely focus on that from that point on. So how our pipeline actually looks like. First, we need to have a CAD model. So we need to actually design the whole thing that we want to print. And in terms of comparison to programming language, let's say Java, this would be something like a Java code, the source code that you actually then compile. You compile it to the STL. STL is actually something like a lingua franca of all 3D printers, where you could, of 3D printing world actually, and you can think of it as a Java intermediate representation. So this is like a jar file that you deliver to the user so that they can run it on a computer. So in our case, the computer is the printer, and the machine code, which is executed there, is a G-code. G-code is something that originates in CNC machines. And it basically is a really huge list of movements of the head. So move to position XYZ, extrude a little bit, move to other position, extrude a little bit, and so on. So that's roughly how it looks like. So if you have an idea, you would like to create something and print it out in 3D, there are different tools for different jobs. Very common choice is Blender. This is an free and open source tool which can be used for modeling. This typically is used for modeling some artistic things, so something that doesn't really need to have very fine, precise dimensioning, but is supposed to look nice because it's like a sculpturing-like tool. If you are doing professional engineering, there is an Autodesk Fusion 360, which is a graphical tool which is designed to make parts, like mechanically working parts, with tight dimensions and do it very fast. The problem is that this is a closed source solution and it's actually commercial, so you need to pay for using this tool on an annual basis, I believe, and this is not exactly a cheap one. So unless you are doing a lot of 3D printing or doing it commercially, this probably will not be a viable solution for you. And last but not least, there is an OpenSCAD, which is a free and open source tool as well. but then you define a final shape that you would like to create in terms of a source code. So this is something really close to our world, the programming world. We have a source code here. So let's try to do a little bit of modeling in OpenSCAD. So what is OpenSCAD? Actually, this is one of these rare cases where when you see a logo of the system, it actually tells you a lot about it. So if you look at it, this is a sphere with cylindrical parts removed out of it. So there are 3 cylinders which are subtracted from it. And this is actually the core idea behind OpenSCAD. You are basically summing up or removing parts of the 3D objects. So this is how the IDE of the OpenSCAD looks like. There is a preview where you can see how how the component that you are designing will actually look like. Then on the left-hand side, you have a source code in which you actually apply commands that shall be executed to end up with this model. And of course, you have a warning/debug window where you can actually see what's wrong with the compilation or what the device's compiler would give you during the process. So you may notice that we used a source code and some 3D objects in one sentences. So what it means is linear algebra. But please don't panic. It's not really complex. Actually, in real life, you will barely ever use anything more than just adding some vectors in 3D or maybe multiplying a vector by a constant. And that's roughly it. So maybe as a first task, let's try to create something simple, like a hollow box which you can put something inside. So first, we start with a box like a regular cube. And this happens to be just a single module used inside OpenSCAD, which is called cube. And then we provide 3 dimensions, OX, OY, and OZ, as a single vector. So it takes a single parameter of a 3D vector and outputs a cube which is of appropriate size. You can also create some constant values, either string or a number or a vector of vectors, whatever you like. And also there are comments which you could put inside the code to make it more readable. So let's try to define some useful constant. So for instance, if we'll be using a size of our box many times, we can create it as a constant and then pass it to the cube. So the cube takes a size, and size is defined as a vector of 3 elements. So we get exactly the same result as previously, but now we have size defined on side. Now let's try to do object difference. So let's try to do this cut-in into our cube to have an actual box, not a brick. So there is a difference module which does exactly that. In its body, it takes a number of elements. The first element is a starting point, and then all the others are being subtracted from the original model. So these are like these cut-ins into the initial part. Here we only have a cube, so there's only one element, and there's nothing to subtract. So again, we end up with exactly the same model. But now, if we add something, we define a wall to be 1.5 millimeters thick, and we define another cube, which will be of the same size as previous one, minus 2 times wall and the vector 110. So this will actually create a vector of a size decreased by a wall and a wall in both OX and OY directions. So this will actually be our internal part. We do not need to decrease OZ because this is only the part of the offset of the box. Because you can see that actually something went really wrong here, right? We created 2 cubes of appropriate size, but instead of a box, we ended up with something like an extruded letter L. So it didn't work. We need to debug it. And there is actually an interesting thing for debugging in OpenSCAD, and it's called hash symbol. So we can put it in front of any object in OpenSCAD, and it will highlight it for you, even though the original object might not be visible by itself, because, for instance, it was something that was being subtracted from the original form. Here, we also shifted up by 1 millimeter up, so that we can clearly see where the part is. And now we can also see where is the problem. So both our boxes originate at point 0, 0, 0, so the center of our axis. So what it means that even though we decrease the size by 2 walls, we decrease it from one end, not from the both as we intended. So this part is incorrect, so let's try to fix it. And to fix it, we use a translate module, which will shift our object by the wall size on OX, OY, and OZ. So now we have this wall thickness all around. And this translation applies only to the objects underneath it until the ending semicolon. So this block shifts the cube, resize it, and put it into the difference so the element is removed from the overall object. So with removing of our debug, let's call it a statement, we actually end up with the box we were looking for, which is great. But you might say, okay, aren't we doing a little bit too much thinking inside of the box, actually? Well, yeah, in a sense, yes. But actually, if you try to design an enclosure, thinking inside of the box is actually the way to go. So let's try to do it. But let's try to do something a little bit more fancy. Let's try to do a rounded box, so the box with a rounded edges, so that it's not sharp. You will not cut your fingers with it because the edge can be really sharp on the edges here. So let's try to do something about it. So first, we need to learn how to use a cylinder. And it's actually fairly straightforward. Again, for convenience, we'll create a couple of constant values, so we know size, and the corner radius. So this will be effectively the radius of the cylinder we are working on. And this will also be the radius of the corner on of our box. And now the cylinder. Cylinder basically takes two parameters, the radius and the height of the cylinder. And this is size of 2. So it actually takes the last argument of the size, which is a value of 20. So now our cylinder is fully parameterized, both with the corner radius and with the height of the box. Now, let's try to create multiple cylinders. And for this, as programmers, we would obviously use a loop. But first, we need to compute what will be the distance between the centers of the cylinders. So again, we take our initial size, and now we need to decrease it by this corner radius on both ends, right? On both OX and OY axis. And now the int s internal size will be the kind of like a box in between all of our cylinders. So having this size compute, let's try to dive into for loops. So dx goes from 0 to 1 with step of 1. So effectively, this will be a vector of two values, 0 and 1. The same goes for dy. And now we are actually computing translation. So it's not a fixed value. It's something that changes with each iteration of the loop. So for OX parameter, we go dx times our internal size of 0. So we take our distance and multiply by the dx, so either 0 or 1. So we effectively are in position or being moved. The same for dy. So we actually get 4 points, which effectively turns out to be the corners of our internal box. And in these corners, we put a cylinder of a specific radius and a specific height. And that's basically it. We have cylinders all over the place. But what we actually wanted to have is a box, right? So in order to do so, we need to create a hole around it. And it turns out there is a ready-to-go module which does exactly that. So for a given set of objects, you can create a shape which is something like a stretch tape all around all the objects that you have defined. So in our case, it's about these 4 cylinders, and the hull will fill up the space in between. So we end up with exactly what we were looking for. We now have the basic shape of the box with rounded corners. But you may notice that we actually will need some code duplications here. Have a look at the original code and the cube usage. So now the cube usage uses a size, but the module cube is already defined in OpenSCAD. So even though the two sizes are different and we need to compute them, the model itself is basically like a copy and paste name. But now we have a model of a rounded box, which by itself takes probably around 10 lines of code. So we will need to copy and paste it into 2 positions in order to do the differentiation between the models. And, you know, remember the oath, you do not copy and paste the code again. What? You did it once, you regretted it, so now we try to move on. So what's the programmer's solution for not copy and pasting code? If you need the same functionality in 2 different places, you obviously create a function. In OpenSCAD, what you're looking for is actually called a module. So let's create a module called rounded box, which takes 2 parameters, our corner radius and size. And inside it, we put all the code that we have used to create this box as a standalone version. And this whole thing is a definition of a rounded box. And now in order to use it, we can just call rounded box, provide the radius, provide the size, and off we go. We have a ready working model. And here you may also notice that I used named arguments. This is an option, it's not a must. In OpenSCAD, you can both use either named or unnamed parameters based on the positions, so whichever notion is more suitable for you. So now we shift from our original simple box, into the rounded box with just changing the name of the module that we are using. Instead of cube, we are using rounded box now, and we're good to go. But where's the definition of the rounded box? Well, it turns out that you can actually put it into a separate file. So we can have a file which defines how the module looks like, and then you can use it in other modules. So this way you can easily create a common code that you will share between different models that you are designing. And again, just for convenience, we create a variable, a constant of value of 8 for a radius that we'll use throughout the boxes. And that's it. That's ready to go, rounded box. And from this point on, actually, it's not really that far to create something like this. With additional loops for doing cut-ins for ventilation, you can actually easily design your own box, which suits perfectly your actual project that you're working on. And some people say that actually enclosures are the killer apps of 3D printing. So you can design any enclosure whatsoever, which matches perfectly what you are doing, and exposing only the parts of the board that you are actually using, which is great. You no longer need to do any custom enclosures that are not repeatable. You can have a model and you can share it with friends, and they can reproduce your results. So we also mentioned at the very beginning that OpenSCAD actually has a logo which is itself designed in OpenSCAD. So maybe let's try to reproduce it. So first, we will define some radius, let's say 20 millimeters, and we'll define a sphere of radius equal to our constant value. But you can immediately see that even though we are not doing anything, we just declared a sphere and a difference for it, it's actually kind of clunky. It's not really as beautiful as the cube that we have seen previously. And that's because of the defaults. By default, the model resolution is fairly small. But you can easily increase it with $fn parameter, where you can assign a different value. You can increase the detail level of the model just by changing that value. But of course, the caveat is that the higher value is, the more precise the model gets, but on the other hand, it also takes more time to compute. So it will take far longer time to actually generate a model which is very, very fine-grained. And in practice, you actually need to have some sort of a balance, because you obviously won't get infinite precision, but on the other hand, the printer itself also has a limit. So it will not produce infinitely precise model. So actually, in practice, this is application dependent. So I often use very different values for instance, for small holes that should have tight fit for a screw, and something else for a part of a sphere, for instance, that should look beautiful when printed and should not have visible edges. So it's basically up to you at the specification. For the purpose of just recreating a logo, value of 150 fits perfectly. So now let's try to subtract our cylinder. So we'll define a helper variable for height, which will be 2 and 5 times radius. Twice the radius is actually the height of the sphere, and the additional extra half is just to make sure that the cylinder actually stands out from our sphere. So we create the cylinder with these parameters. And we actually also need to translate it down a little bit, and exactly by half of the height. Why is that? This goes again to the point where are the center of all the elements in OpenSCAD. In case of a cube, the corner of the cube is in 0.000, so it actually grows outwards. In case of a sphere, actually a center of a sphere is located by default in a 0.000. But in case of a cylinder, the base of the cylinder is in a 0.00, so it's basically OX, OY plane, and it grows upwards. So in order to make sure it's centered, you actually need to offset it by the height, half of the height. And this is a very typical thing to remember for different objects in order to subtract them efficiently. Now, let's try to do the same thing for OY. So again, we create a cylinder, we translate it. So this is actually a copy and paste of the code previously. And there is something new now. There is a rotation. So rotation takes one argument, and this argument is a rotation angles across all 3 axes, so OX, OY, and OZ. So here, what we are doing, we have a cylinder which is upward, and now by OX axis, we shift it 90 degrees. So effectively, it's now in a lying position. So this whole thing, rotation applies to translation, translation applies to cylinder, and we mark it as a debug part so that we can actually see the cylinder, and we end up with what we see on the screen. Now, let's do something similar for OX axis. So we want to have a cylinder across this axis. And this is, again, basically copy and paste code from the previous axis. The only difference is that instead of rotating through OX, we are rotating through OY axis, so that's lying in a different direction. But aside from this, that's it. And of course, last step, we need to mark this one specific cylinder that we wanted to have in order to be an exact match for the OpenSCAD logo. We could, of course, play out a little bit with a correct angle of taking a preview, but technically speaking, we're good. But that's not how you would design a real object. This is something we wanted to reproduce as precise as possible. But in real world, you would probably want not to duplicate the code again, right? So the cylinder and translation, okay, that's no-brainer. This has to be done this way. But the rotation itself can actually be parameterized. So again, the rot value can be a part of the for loop. So we can iterate over vector of vectors. So effectively, rot will get 0, 0, 0, 19, 0, 0, or 0, 19, 0 as 3 distinct parameters. So this loop will actually create 3 objects. So effectively, 3 cylinders rotated in the right directions. So we end up with the model as OpenSCAD is designing. So the only reason we originally started with this copy and pasting code is because it's just a little bit more convenient to mark this one particular cylinder that we want to highlight. But in real object where actually this highlighting doesn't really matter because it doesn't change the output of the print, we would actually go with the for loop. So that's the technique, the way to move forward here. Okay. So you might be asking yourself, okay, so I'm an expert now, right? I know all the OpenSCAD. Well, of course not. We barely scratched the surface. OpenSCAD is really huge. It has a lot of capabilities, a lot of built-in modules, a lot of functions that can compute math values. So you can create really complex shapes in a decent amount of code. What I have shown you is just the basics. So you can think of it by a 20-80 rules. So with a 20% of knowledge, you can actually solve 80% of the problems. And this is actually the great starting point. And to be honest, my first years with OpenSCAD were basically what I have just shown you. So this was like a 90, maybe 95% of my OpenSCAD knowledge, and I managed to live with it for a couple of years. And only recently, I actually started to create shapes which were so complex that the techniques that I showed previously were not enough, and I actually needed something more sophisticated. But if you're designing enclosures for most of the time, this will probably solve 99% of all the cases that you really need in practice. So what are the gains of using the OpenSCAD? So first of all, we finally have a source code for our model, not some binary in some proprietary closed source system. We have a source code. And when we have a source code, we can actually put it in a version control system like Git. So from that point on, we can apply our usual workflow. So we can do a code differentiation. So before committing, we can actually check which parameters have we changed and double check if we actually if we do not try to commit some temporary value that we just changed for a moment for the purpose of debugging, for instance. Same goes for working in the teams. You can now have a pull request, merge requests, and people can do code review. So you do not really need to rely on your friends' words that they have done the right thing. You can actually check and review which lines were changed and how. Which is awesome. Of course, you can also do branching and merging. So now everyone can work on their own branch and then merge into my development branch when they're ready. So what it means, you can also have a continuous integration running. And for each pull request, it can actually build your model. It can also generate previews. Generation of previews is awesome for documentation purposes, because now you can have a model which you generate a preview for and put it automatically inside generated documentation. So you do not need to do any print screen or word descriptions of the model on your own. It just automatically updates with the code. And this is really powerful tool for documenting what you're working on. And in fact, this is also how I generated the previews that you have seen next to the source code in my previous slides. This was exactly it. The source code was actually compiled in OpenSCAD and generated preview. So what you are looking for is a source code and the automatically generated preview. And this is how the slides were made here. Another things that you can use from your regular toolset of programmers are techniques for reusing code. So we already learned how to use modules in order not to duplicate, not to copy and paste the code around. You can avoid hard codes by providing constant values that you use later on. You can have a modularization by moving modules or constant values into a separate files, which you can then use or include inside your modules. And you can play with encapsulation, but even though the OpenSCAD doesn't really support encapsulation on its own, you can have a convention, for instance, like a trailing underscore for a module name or a constant name in order to signal that this is something internal to this file and you should not use it outside of it. So there are ways to go around this as well. So let's see where we are in our workflow. So we have a CAD model. That's great. But we actually need something that we can later on try to send to the printer. So we need to have the STL file, so this intermediate representation. In order to do so, we need to generate STL out of the model, which is like super simple. We just call OpenSCAD from command line. We define what is the output name, the output file name, and what is the input, the source code that we would like to quote unquote compile, right? And this is really as simple as stating that trees don't move, right? So this is a very simple command and it does exactly what it needs, and you can actually script it to automate it. You can actually go even one step further, and you can define that OpenSCAD should be really picky about warnings and make them a hard stop for a compilation. You can enable extra checks for parameters or parameter ranges, which makes even more issues pop up during the compilation stage. So exactly as you do in a normal program. And with this, the compilation warnings shall not ever pass through, which is great, because what it actually means from our perspective is that OpenSCAD is actually our compiler, a part of our SDK, that we are now using to create objects that we will later on 3D print. Now, let's talk a little bit about slicing. So if you remember our pipeline, we now have the STL, but what we really need is the G-code, so something that we can physically send to the 3D printer to do the printing. And the process of generating G-code is called slicing. And the name is actually very descriptive here, because it is literally means take the model, slice it into pieces, horizontal pieces, and for each piece, try to generate the moves of the head in such a way that you will end up with a physical 3D object made out of plastic. And of course, there are tools which does exactly that. So a very common solution is a Slick 3R. I know it's stylized so that it's pronounced slicer, but there is a little bit of a problem with that name because slicer is also a name of a whole class of tools. It's like a car versus a particular brand of the car. So just to make sure we distinguish these two, I will say slicer whenever I mean any tool that does the slicing, and I will say Slick 3R when I am talking about this particular slicer, just to avoid confusion. There's also an open source fork of Slick 3R, which is called Prusa Slicer. This is actually very heavily developed at this point, so there is a really good chance that this will actually become a mainstream. There is also a Cura, which is a very common tool originating from the Ultimaker, one of the very well-known producers of 3D printers. And also there is a Simplify 3D, which is actually a commercial slicer, which used to be outstanding, but actually nowadays most open source slicer also have features in which are present in Simplify 3D. So it's actually losing a bit of momentum here. So from that point on, when I will be talking about slicer, I will actually be talking about Slick 3R. Even though I personally actually plan to switch to Prusa Slicer, and I'm already giving it a shot in some of the projects, I have the most experience with Slick 3R. So for the sake of this presentation and talking about it, I will actually focus on that. But the good news is that if you decide to use Prusa Slicer as well, it's very similar, because Prusa Slicer is a fork of a Slick 3R. It actually shares a lot of parameters, configurations. The look and feel of the graphical interface is also similar. So you should be really good. The switch should be really simple. So let's try a command line switch for generating the G-code. So we call a Slick 3R, we load a configuration, again, define the output name, and define the STL, the model that we would like to slice. And that's it. But you may actually scratch your head, okay, but what's the config thing? Like, where the hell do I get it from? And actually, it's, again, very simple. You can ask Slick 3R to generate the default config for you, and then you can edit it with your favorite text editor. But there is a little catch. Like, if you look into the config, it's actually, this is exactly the default config generated on my machine. It's around 200 options, and some of these options could easily make a full-blown lightning talk, and some of them can actually make a full 1-hour talk just to explain how it works, what it does, and how to optimize it for your particular printer. So there are things which are really not that straightforward. There are nice things in Prusa Slicer, for instance. For each of these options, when you enable Slicer in a graphical mode, you will get a dot next to each option. So you will get a green dot for something which is aimed for beginners. You will get an orange dot for something which is for experienced users, so the advanced option. And the last is a red dot, which is only for experts. So unless you have a lot of experience and you're absolutely sure what you're doing, you should probably not touch these values. So this helps. Another good news is actually that slicers nowadays provide really decent defaults. So if you select your printer type and you select the filament type, the plastic type that you want to print in, the default configurations will probably be 99% okay for your case. And if you are just beginning, they will probably do just fine, and you can just use it off the shelf. Okay, but we were talking a lot about this slicing, but we still do not know what's the output. So you may ask, okay, but just show us the output. And the output looks pretty much like this. So here we have 2 columns of commands, which at the first glance will look a little bit like assembly. And in fact, this is kind of an assembly for 3D printing. So each line defines a command for different purposes. From the top, we can see some setting temperatures, moving axes, for instance, changing the type of coordinates or extrusion speeds and so on and so forth. And finally, we reach the G1 command, which basically goes down through 99.9% of the file. And this G1 command is actually move the head and extrude along the way. So this is like the most important thing in the whole universe. But there is a thing about it. The G-codes are actually very long. So what you see here is probably around 40 lines of some random G-code that I just grabbed out of one of the projects. But the truth is that real files, at least for the models I was recently playing with, was on average around 200,000 lines of the code. So even though the file is perfectly human readable, it's an ASCII text, it's definitely not meant to be read by humans. So in order to see what is going on here, there are tools which can generate a preview for you. For instance, inside the slicer, if you enable it in GUI mode, you can actually have a look into it. There are also standalone tools. My personal favorite is YAGV, yet another G-code viewer, which does exactly that. It visualizes all the commands from the G-code and show how it looks like layer by layer, including all the heads move when the plastic is not extruded. And it shows you the overlay, which is very nice and very convenient to use. There are also some tools which are available online, so you can actually upload your G-code file onto a web page, and it generates a preview for you. So that's also an option. And why is this important? Because when you have a G-code, it's a sharp eye time, because the devil is in the details. And it turns out that sometimes, just by looking at this, how slicing resulted, you will actually learn a lot of interesting things. For instance, you just forgot to enable support structures, and your print will just collapse in the middle. Or maybe you actually enabled supporting even though you didn't wanted support to be there, because it will be hard to remove, and you know that you can print without in this particular configuration. Other things are actually bugs. I recently reported to both Slick3R and Prusa Slicer teams that there is a problem for certain types of geometries and certain infill settings. Instead of getting a proper infill inside of the solid object, you actually get an empty infill. So if you print the top layers on top of it, it will just collapse. So it will effectively break your print. Another common thing is about the details. So sometimes when you have very fine detail elements on the print, which is on the edge or below the print resolution of your printer, you can actually get these details lost. So we can end up with a hole in the model, or something which was really important for you just missing. So it's really good to spend a minute or two, literally, to go through the process and just see if everything went correctly before you actually start printing. Because when we try to estimate the time of the print, you need to know one thing. FDM printing is slow, like really slow. Generally, 3D printing is slow, and FDM 3D printing is like totally slowest thing on the earth, I would say. Just to give you some example, I brought with me a little cube. This is a calibration cube with marked X, Y, and Z axis, and this is precisely 1 cubic centimeter of filament. And this thing printed for like 45 minutes, this little thing. So we can imagine that any bigger printer will actually take even longer. So this is a slow process. So it's really good to invest upfront. And also, it's good to know how long will it actually take, right? So we know this will take long, but how long? Is it like long an hour or long a day or maybe long a week, right? My personal record is a print that fell short of 5 days of printing. So that's a lot of time. But the good news is that we have G-code at this stage, right? So we already know each and every move of a head of the printer throughout the entire print. So we would say, okay, that's great, so let's use it. And thankfully, there is a tool which does exactly that. It's called gcoder. On my Linux distribution, this is a part of a print run package. So we can just call it with Python, provide a parameter of a G-code file to analyze, and you get output which looks something like this. So there are some basic pieces of information regarding the dimensions of the cube inside which the model will print, an amount of filament that needs to be used, and the very last line is estimated duration, and this is something we are looking for. So here we have nearly 6 hours short, like 1.5 minutes, right? So you might say, okay, that's great. So we now have the exact amount of time, so I can just enable a stopwatch and see how precise it is. And this is where dragons lie. The problem is that even though the G-code defines all of the head moves, there are certain things which G-code is absolutely unaware of. Some of these are simple things, like for instance heating time of your heat bed, of your extrusion, of a hot end of your printer. So this is something you cannot tell up front because this can actually depend on the environment, like for instance what's the room temperature. There are even more important things, like things in physics do not happen at once. If you want to have something, some physical object moving at a certain speed, it actually needs to speed up, move at the speed, and then slow down. So if you have some short movements, you will actually be speeding up and just slowing down without actually going with this maximum speed whatsoever. So the firmwares of the printer typically are aware of this fact and are actually compensating. So it's not like the printer is blindly executing the G-code. There is a little bit of logic behind the scenes, and this can actually skew up your results a little bit. So you need to keep in mind that what you get out of the G-coder is actually a lower bound of the print time. In practice, this really depends on the printer. My printer is actually kind of slow one, so in my experience, it's usually between 100 and 150% of the time provided by the G-coder, and how much will actually take depends on the model type. So if there are a lot of short movements, I know that this will actually, this acceleration, deceleration thing will affect me greatly. So this is where I can actually get up to 1.5 times of the original estimation. If the print is simple, there are a lot of stride movements, I know that this will actually be very close to the optimal value that I have defined. So that's good, but you need to keep in mind. And this is, you may say, okay, if something has a 50% chance of missing the correct value, is it of any use? And I say, yes, absolutely. There is a difference if thing is going to take 10 hours or 10 days, for instance, right? Is it going to take an hour, or is it going to print overnight? So for this kind of things, for planning how long the printer will work and when to finish, this is actually a really incredible, important tool. So please use it. Just remember to take the results with a bit of grain of the salt. Okay. So now let's talk a little bit about the pipeline. So we already know that we want to automate things, right? We're software engineers. Our mindset is just designed for automation. And when automation comes in play, we want to have repeatability. And let's rise the bar even a bit higher and go towards reproducible builds. We're software engineers, so we basically know what reproducible build is. But just to make sure everyone's on the same page here, let me quote Wikipedia. Reproducible builds, also known as deterministic compilation, is a process of compiling software which ensures the resulting binary can be reproduced. Simple code compiled using deterministic compilation will always output the same binary. So, long story short, instead of instead of having build results which just happen to be the value that we computed at this particular point, if we have a reproducible builds, it doesn't matter if I build now or in 3 years' time, we will actually guarantee to get the same binary result each and every time. So if you look from this repeatability and automation point of view, we actually have pretty much all the bricks in place. So now let's try to glue them together. Let's try to make it happen. And by make, I mean GNU make. So this is an example makefile, which is actually fully working and functional automation for building the whole pipeline. So starting with the model and ending up with the G-code. So of course, GNU make is quite a complex tool, and we definitely have no time to go into details here. So instead, I will just give you a glimpse so that you can understand the basics of what is going on in this particular piece of code. So first, we list all the SCAD files, so the source files, and write it into SCAD's variable. Then we define the file names of all the G-codes. So basically, we take all the names of the SCAD files and change extension to the G-code so that we now know which files we are looking for. And we define a target all, which will be the default one, and it depends on all the G-codes. So it basically tells make, please generate all the G-codes. Now, how the make knows how to make a G-codes? Well, we just tell it. So we tell that STL can be created out of the SCAD, and the SCAD file can be pre-computed into the STL using following OpenSCAD command. And aside from obvious parts of defining output and input, there is also an interesting thing in the middle. -d tells OpenSCAD to generate the dependencies files. So it's something similar to GCC's -md flag, which defines the dependencies for files in terms of includes. And a similar thing can be done for OpenSCAD, and you can this way track the dependencies. So if you are doing then incremental builds and just changing some of the files, some models, the makefile will now know how which files need to be rebuilt in order to get correct final results. So that's great. Now, the G-code itself can be generated out of the STL file. And for this, we know the Slick3R will do the trick for us. The config, we just put in the same directory. Now, we also generate a dummy target called time, which depends on all the G-codes. And for all the G-codes, it runs a gcoder with the file name. So this will effectively output printing time from the gcoder for each and every model that we want to print. Then, of course, the usual clean target, just to make sure we get rid of everything that we have generated. So we remove the dependencies, the STLs, and the G-codes. So we are basically back to clean repository. And the last but not least, we include all the dependencies files if they are there. So if there are no dependencies, we build for the first time, nothing happens. But if we do incremental builds, this is the line which will make sure that make is actually aware of dependencies between our SCAD files, source codes. So the usage is fairly simple. Let's create some 2 dummy SCAD files. Each of them will create a cube of a given size. And then we just call make. Make by default will call an all target here. So all the G-codes will be created. Then we can call make time. And we get all the timings for printing. And we have actually the models and the time. So we are ready to print. And this is actually something totally awesome from my perspective, because it means in 12 lines of code, we can actually get a fully automated and working pipeline for working with source codes to generate the actual G-codes for the printer. But of course, there is one catch. We talked about reproducible builds, and our SDK can actually change. If we run the same commands with the same makefile, in 2 years' time from now, we'll probably have a newer version of OpenSCAD, we'll have a newer version of Slick3R, and we will effectively get a different result out of it. So in order to stabilize SDK, we will use Docker. So we'll try to containerize our whole build. And this can again be done simply with a short Dockerfile. So we are using Debian 11 as a base. Then we say to install additional packages. And the 6 core packages that we list here is actually all that is needed to make sure that our makefile is actually working. Now, in order to use it, we need to build the SDK. Then we can run a container using the image that we have just created, run it as a current user, and use the SDK which has been built. And we get an interactive prompt where we can type in the commands. So we can type make, all time, clean, or any other targets that we want. And with this step, we actually have SDK fixed in time as well. So now we have fully automated and reproducible builds for our 3D printing. So if you have used Docker in the past, That's great. The last 2 slides were absolutely easy for you, and it was a breeze. But actually, if you have never used Docker, I have a good news for you, because right after this talk, there will be a Docker Love C++ talk, and where Piotr and Adrian will explain you how you can use Docker to create SDKs for C++. And actually, like 90% of this knowledge will also be applicable here. So with these 2 talks combined, you will understand every single bit of automation and repeatability and reproducibility that I'm talking here today. So we have automation, we have repeatability, so we're all done, right? Well, of course, you know, in real life, one size doesn't really fit all, usually, and the same goes for 3D printing. And if you start using this pipeline, which actually is a pipeline which I originally created when I first started my adventure with 3D printing, something like half a decade ago, maybe a bit longer, but you will quickly realize that you need to have some points where you can variate things. So, for instance, you will print with different materials like PLA, PTG, TPU, and others. They require different temperatures, different print speeds, and this needs to be taken into account. Another common thing is printing for different properties. So you can have a draft print where you are just interested in rough object overview, and you're just interested in getting the print as fast as possible. You can have a pretty print where you are going into the fine details, because this is something like a sculpture that is supposed to look pretty. You can print for strength, so for something that will actually work mechanically. I very often do waterproof printing, so something that shall not leak in or out water. And all these profiles actually have conflicting interests. So different parameters need to have different values to make things work. And there are other more nuanced details that you will probably also find along the way. So in order to kind of stabilize it, I've created a 3D printing SDK project, link below and a QR code if you want to check it now, which basically provides all the basic functionality here. So it has a Dockerized SDK, it supports both OpenSCAD and raw STL files, so if you just download an STL that you would like to use as a part of your project, then you can also include it, no problem here. It supports multiple filaments, it has different build modes, so for instance, this waterproof versus having a fast draft print, and so on. And it also offers extensible interface, so it's fairly easy for you to actually add the new filaments or new build modes into the system. Okay, so we are slowly approaching the end. So let's quickly summarize what we have learned today. So first we did a little bit of an introduction into the 3D printing so that we have common base ground where we are. Then we learned some basics of OpenSCAD and slicing concept so that we know how to work with these tools, at least on a basic level, and how to automate it. We also estimated the print time, and even though the estimation is not perfect, it's actually giving us really good insights into what to expect. And last but not least, we automated all of this in order to have reproducible builds each and every time. Now, what should be the next steps? Well, I would highly recommend you go into Mastering OpenSCAD book, which is an open source book. You can read it online for free, or you can order a paperback version from Amazon, I believe, which goes through 10 example projects, each of them showing different techniques in OpenSCAD, which you can actually apply. So this is actually a great boost of OpenSCAD knowledge, showing a lot of tricks and techniques how to make the code readable and how to make it compact and yet solve complex problems. So I highly recommend you go through this. Now, there is a knowledge bootstrap, so there are a lot of links on the internet. When I was starting with 3D printing, there was barely anything aimed at beginners, but nowadays it's not the case. There are a lot of things, so I provide you some links. If you can now do a print screen and just go through the links offline. And if you want to wait after the conference, these materials will also be available, so you can then click through them. But the long story short is the internet is full of really quality pieces of information nowadays, starting from beginners going to advanced users. So pretty much anything you need to know is out there at the reach of your search engine. Okay, so if you want to do print screen, please do it now. I'm changing slide in 3, 2, 1, and it's gone. Okay, so thank you very much for your attention. That will be all from me. I hope you found this talk interesting, and I sure hope that you will actually try it out at home, because, remember, it's always good to try out new things. Thank you very much, and enjoy the rest of the conference.
This was Bartosz Szurgot talking about 3D printing. Don't forget about our virtual escape room. Check our website right after the conference. Hackdive is waiting.